All right, everybody. My name is Jason Bialik. I'm with Tech Sales with Honeywell, and we're excited to be able to bring you uh, well prepared and well thought out presentation on how to operate the RDR-4000 and 7000. Both of those radars are volumetric radars, so there's some unique aspects to them that we'd like to share with you today. Eric Tobler, who's one of our corporate pilots flying out of the Southeast, has quite a bit of experience, both technically and as a pilot on these radar systems. We'll have Roland, one of our tech fellows, joining as well. Ryan Goldstein is with me on the tech sales side and quite qualified with respect to field service engineering and aircraft installations and all of that. So the primary focus is on operating the radar. However, we do have some technicians in the group. And so I would expect we may end up at the end of the call, at the end of the webinar, getting some questions. We're going to do our best to keep the answers to the questions short for the benefit of everyone on the webinar. We'd like to give everyone an opportunity to learn as much as you can and get your question in toward the end. So if it tends to get into a lot more detail or requires a more thorough answer, we can always do that separately from the webinar, and we welcome that opportunity. So this really is all about you guys out there, the pilots and maintainers who are using our system. We appreciate all of you. And without further ado, I'll let Eric take it away.
All right. Thank you so much, Jason. And thanks to everyone who has joined today. And again, just want to add my welcome to this webinar, again, for the RDR-4000 and 7000 weather radar systems. And as you probably know and would, I think, vouch for, that radar plays a pivotal role in safety and providing us with real-time information. So we're going to talk about some important things today. We're going to show uniquely how these radars show on-path hazards and much more detail on areas detected as convective weather. And we'll talk through some significant advancements in technology as well that, again, just hopefully will allow you as pilots to navigate more safely through any kind of changing weather conditions. Please be aware of the confidential nature of the webinar along with our export compliance classification for the same content. So again, my name is Eric Tobler. I'm a technical pilot. I've flown and trained pilots on different regional and air transport category aircraft. And I am being joined, if I believe Mr. Roland Zito, if you have joined. Roland is an engineer. Thank you, Roland. Yeah, good morning. Roland Zito is an engineering fellow and truly an incredible source of knowledge on our weather radar and radars in general. So thank you, Roland, for supporting us. And also we are joined on this call by Mr. Eric Anderson, who will be moderating the session and assisting with any questions that may arise at the end of the presentation. So please take note of any questions that come to mind during the webinar, or you can also use the QA box feature in the webinar window to submit a question, and then again, we can take time during the final 15 minutes to address as many of those questions as possible.
Thank you, Eric.
So today's webinar presentation, we're going to delve into weather radar systems, as we mentioned, and specifically provide you with operational insights for the RDR-4000 and RDR-7000. We'll explore limitations first, followed by our patented 3D volumetric memory buffer for automatic features, functions, operational modes, and some practical applications, including what happens to the radar during GPS jamming and spoofing, which I think has been definitely a popular topic recently. Overall, enhancing your understanding of how these tools function to ensure safe skies, weather avoidance, and really just giving you more confident flight with this onboard tactical weather radar. That is our objective today. I do want to mention, please note, be aware, the availability of some of the features that we discussed today will depend on your specific installation or configuration, and some of them may also be a system option. So they may not necessarily be on your aircraft. All right. So weather radar technology has evolved significantly, with modern systems offering capabilities beyond what earlier, or maybe I'll say like older radars could achieve. So the RDR-4000 and 7000, operational for a few years now, particularly the RDR-4000 since the late 2000s, has been continually updated to incorporate advanced features such as automatic scanning and enhanced turbulence detection. So keep this in mind. So by the end of this webinar and training, you should be able to answer these "did you know" questions. And by the way, the radar will do the following all automatically. And so you'll see these insights in the second half of my presentation, but essentially this is what we want you to know. And so we'll cover these topics. The weather radar automatically scans weather and ground map information into a 3D volumetric memory buffer. It offers automatic control of the antenna tilt for reduced workload. Did you know that it also corrects for Earth's curvature, has predictive hail and lightning functions, supports radar shown on vertical situation display, detects convective turbulence, differentiates between on-path and off-path weather, and helps with analysis of storm cell height by selected altitudes. Again, we'll explore all of these useful insights during the training session. I've marked those slides later on, again, with the little star that you see in the top right that says Insights. So hopefully those will be good takeaways for you. And lastly here, before we continue, I'll mention just one of the most profound elements of both of these radars, which we're going to talk about, is the automatic tilt adjusting technology using proprietary software to repeatedly and automatically collect and store data for up to 17 horizontal scans into a 3D volumetric buffer. So updated completely every 20 to 30 seconds, the radar interfaces with the aircraft's anticipated flight path, and through this 3D volumetric memory buffer, which is the true heart of the system. I think, Jason, you had touched on it as well when you made your introduction. We're able to correct stored weather information to properly display it for you, even correcting again for Earth's curvature and with compensation for ground returns. Again, we're going to cover all of this information for you today. But first, before we get into that, I do want to mention and talk about what are the weather radar limitations and what can it not do, just for clarity. And we won't spend too much time on the fundamental basics and principles of weather radar, but quickly, what does a weather radar primarily measure? It measures reflectivity, mostly from liquid precipitation. Again, it's reflectivity mostly from liquid precipitation. Indirectly from that, we can calculate rainfall rate. The weather radar measures how much of the transmitted energy is reflected back to the radar, and that amount of energy reflected is proportional to the rainfall rate and is represented by different colors utilized on the display. The display correlation to approximate rainfall is based on a decibel level and appears as follows in this table. Weather targets are color-coded by intensity of the return. And again, we're going to touch on a little bit of this later on. So in general, what does the radar not measure? As a friendly reminder, the radar will not sufficiently reflect and detect water vapor or clouds, fog, very frozen storm tops, volcanic ash, dry hail, snow, or clear air turbulence. In contrast, rain, wet hail, and wet snow are very good reflectors of radar energy, but dry hail, for example, only returns 3% of the energy that a raindrop returns. So maybe think about the following is that pilots may see a cloud mass and think that it should appear as a radar return on the forward display. Large cumulus clouds may be a developing storm cell, but will not necessarily show on the radar until there is sufficient size and quantity of liquid water droplets available. Or differently, maybe in a different scenario, immediately after a storm has dissipated with little to no rain falling, a dark cloud mass may still exist, but there may not be enough reflectivity available for it to appear on the display. This is where, for example, onboard weather radar may differ significantly from a ground-based radar source, and that data could be even 15 to 30 minutes old as well. We're going to cover more on that a bit later. Before we continue with more discussion on the operation, I do also want to mention, this is important, a few things about antenna size. There are different sizes for the RDR-4000 and RDR-7000 weather radars, and there are some limitations because of that. So let's talk about this table. Starting on the far left, we show a few different example aircraft types and their respective antenna size installations in inches, followed by the related beam width in degrees. And then moving further to the right in the table, we show the width of the beam in feet at different nautical mile distances away from the radar antenna itself. Relatively speaking, smaller antenna sizes are unable to concentrate the beam energy as well as larger antenna sizes. This is related to physical area available to intercept or receive electromagnetic radiation or radio frequency RF energy. Smaller antenna sizes result in both a wider beam width and not being able to detect as far because of the lower peak gain of the antenna pattern. So beam width and antenna gain are both key for weather radar performance. With the bigger beam width on the smaller antenna sizes, it translates to a lower resolution in the crossbeam, making it more difficult or potentially more difficult to distinguish two separate cells, particularly in the longer range. So in other words, I'll mention, notice that at certain distances from the antenna, shown on the more on the right side of the table in the pink boxes, the beam width is actually larger than the 60,000 foot upper limit of the 3D volumetric weather buffer. At those distances, even a very large storm may only consume around half of that beam width, essentially causing what is known as range attenuation or a perceived signal loss. Another thing to mention here as it relates to both of the last two topics I touched on, which was essentially talking about, what does the radar not see and just the antenna sizes. So I want to mention this, that many of you now have a tablet or EFB that can show strategic weather from ground-based radar. A few things to remember when using such weather information when comparing to the onboard weather radar image. First of all, the colors used, and I'm comparing left side and right side here, the colors used may not be one-for-one mapping for the reflectivity level, meaning our green, like on the left, may not be at the same intensity levels as what I'll say their green, or maybe, for example, our yellow on the left could be the orange on the right. And so in general, there may be also more colors used. You can see on the right side, the range of coloration is much broader than what's seen on the left, which uses red, yellow, green, and black. I'll mention too, notice on the right side that the darker blue colors represent precipitation below 20 decibels. That equates to less than 0.028 inches per hour. Our weather radar shown on the left does not show that rainfall rate below the 20 decibel level. It's shown as black. Take away all those teal and blue colors, and the two images do begin to look a little bit more similar to one another. Consider also that the refresh rate is on the order of 5 to 10, even 20 minutes sometimes for ground-based radar on the right versus the 30-second refresh rate from the onboard tactical weather radar, again shown on the left. The weather images are taken from a different perspective as well. So ground-based radar, as you know, is looking up from the ground. Ground contamination is less of an issue or a challenge. Airborne radar in certain phases of flight has to look down. So the radar return on the left may contain ground returns in addition to weather returns or vice versa. Again, in general. When in doubt, use the test mode. So this does serve as a functional check of the installation. It can be used on the ground or in the air. It's good practice to run the test sequence after system power up and when the avionics are ready for flight, of course. And again, can be performed by the flight crew or by maintenance personnel. The test sequence may be run at any time. If in flight, just keep in mind no actual radar tests are performed by the system, but the test pattern is displayed. And then on the right side as an example, just to illustrate that it does show any current faults if there are any. Notice the test pattern on the display in the example on the left. The test pattern shown depends on the installation and will indeed vary from configuration to configuration depending on the aircraft that you have this installed on. All right, so the moment that hopefully you've been all waiting for, we'll talk about the weather radar, what it can do. Now, if you don't mind, as a point of emphasis in legacy or conventional radar systems, and I think this will set up the next discussion here as to what can the RDR-4000 and 7000 weather radar systems do. So with older radars going back, there is a one-to-one real-time correspondence between the side-to-side movement of the antenna and the respective image being updated on the display. So again, in these older systems, as you may already know, the display is synchronized to the antenna tilt and sweep. In contrast, though, the RDR-4000 and 7000 systems have eliminated the limitation. The mechanical scanning pattern of the antenna is decoupled from the weather images shown on your displays. Again, the radar system, the RDR-4000, 7000 continuously scan the entire space in front of the aircraft and store that data in a 3D memory. The memory is continuously updated with reflectivity data from new scans, and the data is compensated for aircraft movement during maneuvers. The data is extracted from memory to generate the selected views without having to make and wait for view-specific antenna scans. Again, we're going to get into all of this in further detail. But important to remember, we are definitely pivoting into a completely different architecture with RDR-4000 and 7000 with the decoupling of that scanning pattern and from what is shown to you on the displays. So while in flight, the Honeywell weather radar is always scanning so that the most current weather information is instantly available in a 3D volumetric memory buffer, which that's what is illustrated here. Using the weight on wheels system or other qualifiers, the radar is off and the aircraft is on the ground and the system is set to test mode, or the weather display is deselected on both sides and predictive wind shear qualifiers are not satisfied. And again, the radar is on while the aircraft is in the air, regardless of any other settings. It's always on. So the data stored in this 3D volumetric buffer you can see in this video is organized in 3 dimensions by latitude, longitude, and altitude, and is larger than the displayed area potentially, with stored buffer information even being behind the aircraft, could be behind the aircraft. I'll play that one more time. And I'll continue too. So antenna scanning algorithms are then used when comparing weather in the buffer with the aircraft's flight path, and when analyzing weather when utilizing constant altitude slices. We'll talk about that shortly. For each location in the 3D buffer, the system also stores associated information like range, reflectivity, turbulence, and whether the returns are coming from weather in the atmosphere or from ground. All right, so here is where we start a little bit more of that conversation about takeaways and some of this operational insight for you. One of the first things that pilots should notice about RDR-4000 and RDR-7000 is that there is no direct tilt control, because again, the system is automatically and continuously scanning and collecting weather and ground returns. Since there is no direct tilt control, the pilot is not using the control panel to control the radar antenna's angle, but rather using the controls available to request information to be displayed from the 3D volumetric memory buffer in different formats, or what we call buffer modes, based on flight path. Depending on your control panel configuration, there are just a couple of examples here. The weather radar system may be able to then further provide pilots with independent selections of range, modes of operation, gain setting, and even specific weather at selected altitude. We're going to talk about that detail in just a little bit. Depending on weather intensity, antenna size, and flight altitude, this can be captured from the nose, the reflectivity can be captured from the nose of the aircraft up to and out to 320 nautical miles at most, and from the ground up to 60,000 feet. Scans above the freezing level are adjusted with additional gain automatically to make less reflective and potentially frozen storm tops to be more visible on the forward display for you. In other words, the result is a presentation of weather information that is intuitive, improves awareness of the entire weather situation, and reduces the potential for misinterpretations, thus reducing your crew workload. Let's talk about on-path versus off-path weather interpretation and how that's displayed. Separation of on-path from off-path weather is based on several parameters, including the aircraft's altitude, phase of flight, flight path, and any presence of convective weather. The separation is done by applying an envelope around the intended flight path. Weather within the envelope is considered on-path weather, and then weather outside that envelope is off-path weather. So let's talk about how this flight path envelope is calculated and what falls into this special zone. The nominal flight path weather envelope is plus or minus 4,000 feet with respect to the expected flight path, shown in magenta here on this slide, with absolute limits at 0 feet and 60,000 feet. And again, plus or minus the 4,000 feet from the flight path. The flight path is computed based on the ratio of vertical speed to ground speed. The expected flight path altitude is extrapolated out to 60 nautical miles. And beyond 60 miles, level flight at the calculated altitude would be assumed by the weather radar. Again, an envelope is placed around the projected vertical flight path by plus or minus 4,000 feet, and then compared to the weather returns in the 3D volumetric buffer and subsequently displayed. If the weather falls vertically within that envelope, it's considered on path. If the weather is outside the vertical envelope, it is shown as off-path weather. And I'll show you examples of displays and how we show both of those differently. So you might be asking yourself, does that capture all of the important or hazardous weather? That's what you might be asking that. Well, the envelope boundary limits are dynamic as they are expanded if convective weather is present or is observed. If convective weather is present, and to ensure that relevant convective activity is displayed at cruise altitudes above 29,000 feet, the floor of the envelope is actually extended down to 25,000 feet. Again, this occurs when the weather radar detects vertical development and will subsequently extend the on-path envelope. It'll go down and make sure that it's including that area. On the ground or during departure or approach, the ceiling of the on-path envelope is fixed at 10,000 feet. This provides approximately 10 minutes of look ahead. But again, with any vertically developing or developed weather, this on-path weather boundary would actually go from that 10,000 feet and extend up to 25,000 feet in those areas, like is being shown with this illustration. You've seen the image here on the left. I'm going to tie these two things together. So I want to tie together this weather that is dependent on flight path with on path versus off path, and then going back to the 3D volumetric memory buffer. So again, keeping this 3D image in mind as we continue to discuss. So to begin with, be aware that the three-dimensional data that's illustrated here on the left half is translated into a two-dimensional display for you in the aircraft, which I'm representing on the right half side of the screen. From the 3D volumetric buffer, columns of weather radar data are collected and then translated into the display image for the pilot. So in general, the weather displayed for any one memory cell is the color of the strongest return in that column of memory cells. Specifically, if there's any weather data in a given column that is inside the envelope for on-path weather, the color of the strongest of those returns will be displayed. If there's no weather data inside the on-path envelope, then the color of the strongest return from outside the envelope is displayed as secondary weather. So in this illustration, showing 4 columns of weather data, column 1 would obviously just show the one cell, off-path yellow. Again, that's represented both in the columns and then on the right, that two-dimensional, those 4 squares represent your two-dimensional display. So box number 1 would be off-path yellow. Column number 2, let's look at this one, a bit more interesting. It has both on-path and off-path weather, definitely more vertically developed, and could be considered convective with that vertical development. So column 2, when it appears on your display, it would show red. Column 3 would be off-path green. Column 4 would represent itself Now, notice column 4 has yellow, but that yellow is off path. So therefore the on path green is displayed. Any weather shown as on path should be considered for additional analysis, particularly as the aircraft continues to get closer to that area of precipitation. Partly why we do that, again, remember, the on-path weather could potentially include vertically developed convective weather. So we definitely want to be showing that. And if that is the case, there are other ways that you can analyze that further, and I'll get into that in a moment. So remember, in automatic mode, the weather radar packages the data in the 3D volumetric buffer with correction for Earth's curvature and ground returns, and subsequently displays that data relative to the aircraft's vertical flight path, essentially a summary of what we've introduced. The radar displays weather along the flight path envelope known as designated flight path weather or on-path weather. We've mentioned that, and here's how it shows it on the displays. On path would be using solid colors. All other weather is designated as off path or secondary weather and is displayed with black stripes through it, or appears what you may hear as hatched. Secondary weather is displayed for situational awareness and to aid in making changes to your flight plan to avoid flight path related on-path weather. The weather radar is essentially telling you or the pilot that if the atmosphere has enough moisture and energy to push weather above 25,000 feet, again, shown in a solid color, that weather should be monitored and may require further analysis. There may be cases where the pilot only sees solid green above 25,000 feet, like in the example I gave on the previous slide. But remember, the flight path weather always has priority over and covers off-path secondary weather, which could be yellow or red. In this scenario shown, you may be able to stay on your planned route of flight. In auto mode, both on-path and off-path weather are shown. On systems with any on-path only mode selection, sometimes referred to as WIXP, the off-path weather will not be shown. Only on-path weather is shown. So kind of toggle back and forth between those two. If you were to just want to see the on-path weather, some installations allow you to do that. Again, be aware that the on-path weather always has priority over and covers secondary weather that would have otherwise appeared on the display. It's very important to consider, because of this, the weather radar system may at times appear oversensitive or not sensitive enough. But the key here is to think about altitude first, or on path first, and then the color. So if something is on path, it's definitely something to keep an eye on, something to monitor, and potentially do some additional analysis on, which I'll get to here in just a moment. All right, here's another important takeaway for today's webinar. Did you know the weather radar RDR-4000, RDR-7000 corrects for Earth's curvature? So what does this mean exactly, and why does that matter? Well, the problem for most radars begins with the Earth being curved and the weather following that curve, of course, and also something called the radar horizon, where some or all of the weather at long range may not be visible to the radar at all. So notice in this example illustration showing a legacy radar system with a single beam, you would reflect off of very different parts of 3 storms, which are essentially the same size to one another. through the middle of the first. So the beam would cut through the middle of the first one on the left, the frozen top of the second one, and potentially be well above the third. But as you very well know, our flights are based on relative movement, flying a constant altitude above sea level, or at least as it pertains to a pressure altitude level throughout most of the flight, like during cruise. So the effect of Earth's curvature on weather radar returns can be quite significant if left uncorrected. Take an example with an aircraft level at 25,000 feet, with its radar beam also at an average of 25,000 feet. Because of the Earth's curvature, the center of that radar beam at 60 nautical miles away from the aircraft is at or slightly above 27,000 feet. It's almost 37,000 feet at 120 nautical miles away, which would be another 60, and then 44,000 feet at 150 nautical miles. So the resultant display of these three cells using the same beam angle would show three very different situations, even though all three cells in the example are of the same size and level of hazard when truly compared to a constant altitude above sea level. So bringing this full circle, the display of weather from the Honeywell weather radar system, which again, it will vertically interleave all of these scans together, and it's shown with respect to weather relative to the aircraft's vertical flight path in a flat layout. So that would provide a much more pertinent information and data to the pilots relative to the aircraft's actual flight path. So again, the reflectivity is collected in the 3D volumetric memory buffer, and then because of that, we are able to correct it for the Earth's curvature. Here's another very interesting and unique technology for ground clutter suppression. And again, this is a benefit of the 3D volumetric buffer. An internal terrain database uses a version of our industry-leading EgyptWiz database, and that's utilized in the weather radar to help reduce ground clutter in weather displays and to reduce weather returns from the ground map display. Think of this as a three-step process. So step one, collect all of the data from the ground map display. I'm sorry, step one, it would be collect the data from both the weather and the ground, so just in front of the aircraft. Step two, place that data into the 3D volumetric buffer. Step three, use the terrain data to essentially remove ground clutter. So the terrain database allows the radar to distinguish between weather and ground returns, so we can then display only weather information in the weather mode and only ground returns in the ground map mode. Note, however, the database, or just be aware, the database does not know man-made objects such as buildings, airports, or cities. The benefit is that the ground does not really change, obviously, as that quickly, and therefore does not require frequent updating to that terrain database that's inside of the weather radar. Okay, so I've alluded to this one a few times, talking about further analysis. So if you are seeing weather that is on path, particularly if it's yellow or red, definitely we encourage you to do some further analysis, and that can be done with this constant altitude level weather analysis mode that's provided with the both RDR-4000 and RDR-7000. Now, sometimes this is referred to as manual weather mode, and this constant altitude slice mode provides a means to assess storm cell height and development by manually selecting altitude slices. Again, sometimes referred to as manual weather mode. I think that comes from some of the weather radar cockpit control panels, which have a man setting. essentially to do this function. So recall that data in the 3D volumetric buffer is corrected for the Earth's curvature, like we discussed. And that's why we can call this mode a constant altitude slice, as it's based on a true MSL altitude. When the pilot first enters this mode, so here, for example, this is just one to illustrate from the Gulfstream Symmetry touchscreen control from altitude select auto and going into manual. So in this example, we're showing moving the slider to different altitudes. And so you can select different altitudes. Again, I'm simulating this a little bit on my side. I'll toggle through it a few times, but you can go 1,000 by 1,000-foot increments from ground level all the way up to 60,000 feet. You're essentially still in automatic radar mode, but utilizing the buffer, you are now looking at a particular altitude, and any weather present in that horizontal slice is displayed. So again, as a technique during normal ops, if your radar installation permits, I would strongly suggest one pilot should be in auto mode, while the other pilot can be in this constant altitude buffer mode. And this is just an example from the displays where you might see, for example, on the left side, 14,000 feet, and then on the left side, 27,000 feet. Bear with me just a moment. I need to switch my audio. Sorry, everyone.
So while Eric is working on his audio, we can start addressing some of the questions that have come up in the Q&A. First of all, will this presentation be available for future viewing? Yes, it will. This recording of this session will be delivered to all the attendees via email, and also the presentation will be posted under the webinar section on our portal. Second of all, why was the LX Hail feature removed? No longer an option on symmetry aircraft. I'd like to ask you, Ryan or Jason, to discuss that. Could one of you talk to that question?
So that may have been a Gulfstream OEM type decision for simplicity of crew operations. I'll need to get an answer for you, Eric.
Okay, so Chris will follow up. Jason will follow up with an answer. Chris Meyer was the guest who asked the question.
And I'm back on if you can hear me, Eric.
Thank you, Eric.
Thanks, Eric. Go ahead and please, we've addressed both the questions in the chat right now, so please continue.
All right, sounds good. Thank you. And sorry about that. I was just having trouble with my audio and just wanted to switch. So, okay. And you can still hear me okay, Eric?
Yes, sir. You're good to go.
Okay, thank you. All right, so let's talk about the hazard features. Rain is typically not the hazard itself, although heavy rain and or a combination of freezing temperatures can be of concern for obvious reasons, such as runway contamination, engine flame out, and icing. But more commonly, what needs to be avoided is hail, lightning, and turbulence that is associated with convective activity. So, would you believe the radar system can also show you this? Basically, predictive hail and lightning. It specifically can show areas, predictive hail and lightning, and detected areas of convective turbulence as well. So if the hazard display configuration of the radar system is installed, icons will be displayed on top of the precipitation reflectivity to identify areas that have signature characteristics of hail, shown with the lollipop, or in some installations as a triangle, and then lightning shown with a zigzag. The radar does not directly detect hail or lightning. It uses a proprietary method to analyze the data in the 3D memory to identify areas that have a high probability of containing these hazards. Hail and lightning icons indicate that conditions in the associated weather cell are conducive to the development of hail or lightning, respectively. They do not guarantee that hail or lightning will be present, nor does the absence of an icon guarantee that the condition will not be present. So treat the entire weather cell or area as a threat. All right, note that, sorry, I was getting an echo. Okay, is that better?
Yes, Eric, that
Okay,
works.
thank
And it wasn't too bad when it happened.
Note that an icon cannot indicate the exact location of an expected hail or lightning, and icons used are all the same size. Usually icons will be smaller than the reflectivity region, but at longer ranges, this may not be the case, and a color region may be covered by an icon. But most control panels and configurations do have a hazard button to help you declutter. With an icon present, these areas are considered, again, convective or hazardous and should be avoided. Switching a little bit over to the turbulence side. So turbulence detection is an automatic function. Turbulence information is limited to the first 40 nautical miles or 60 nautical miles if the hazard display config is installed. And it's displayed for convective turbulence within plus or minus 5,000 feet of the aircraft's altitude. Turbulence within this range and inside the flight path weather envelope will be displayed in magenta. The turbulence data is represented in a block shape, helping to visually differentiate it from reflectivity data. The turbulence detection feature of the RDR-4000 and 7000 is quite sensitive as compared to previous radars. On avionics systems with a vertical situation display, the auto mode shows a vertical slice of the 3D buffer, either following a flight plan or along the true track angle, if flight plan information is not available. This will give the pilot a quick view of the weather in all altitudes within the 3D buffer and displayed out to a certain distance, typically, again, on the vertical display, typically out to 100 nautical miles maximum. With some installations, the weather radar display can be controlled to show a vertical slice of weather on the VSD based on a specific azimuth offset. The azimuth offset, as shown again in the example here by the gray line on the map, represents where the weather is being depicted on the vertical situation display. Again, adjusting the azimuth does not change the scanning aspect of the weather radar. Adjusting the azimuth manually is just a display control function only. Let's talk about attenuation. So with the react function or rain echo attenuation compensation technique, this indicates areas where attenuation of the radar signal, known as radar shadowing, is severe enough to degrade the ability to display weather behind significant intervening weather. As the transmitted radar signal travels through heavy rain, it loses power or becomes attenuated. So if this attenuation is severe enough, weather behind a storm cell may not be detectable, or it may be displayed as being less severe than it is. For example, it could be green instead of yellow. The hazard display configuration of the radar automatically indicates both by azimuth and range areas where the radar signal has been attenuated. These areas are shown as magenta arcs, superimposed over the reflectivity in the specific areas where the signal attenuation is significant. Again, the arcs don't just show a range location, but also a specific azimuth for each individual arc. Here is an additional separate example of the vertical situation display with react symbology. These arcs indicate that there could be severe weather in that area, even though only mild or no reflectivity is shown. In areas where a react field is shown, expect the possibility of weather that may need to be avoided. Let's discuss now a much more recent topic of how the RDR-4000 and 7000 weather radars may be affected by GPS jamming and spoofing. As discussed earlier, the weather radar uses GPS latitude, longitude, and altitude based on mean sea level to establish the reference point of the aircraft for the radar returns in the 3D volumetric buffer. The latitude and longitude are used to look up the terrain elevation from the built-in terrain database. This information is used to separate the radar return between weather and ground. This is required to, again, produce the weather mode displays that are free of ground clutter. The weather returns are inserted into the weather buffer, and in contrast, the ground returns are inserted into the terrain buffer. So altitude is used for the weather radar ground separation and inserting the radar returns into the corresponding position in the buffer. One other purpose is to compute the set of tilt angles for collecting the radar returns. So all three dimensions, latitude, longitude, and altitude, are definitely important parameters for the weather radar to know. So potential effect of erroneous position or GPS jamming spoofing here with erroneous position PPOS data, particularly when unflagged, creates a misleading misregistration of the terrain data with the radar echo return data, potentially resulting in either ground returns erroneously being displayed on weather mode display. This is referred to as ground bleed through, occurring, for example, if the erroneous terrain data values are low compared to the true terrain heights, or missed weather detections, for example, if there happens to be erroneously high terrain elevation data values in the location of true weather. So you essentially could be getting the indication of ground when it's weather or vice versa. Another potential effect of erroneous GPS position arises if the position value itself changes suddenly by approximately 5 nautical miles or greater. The weather radar software detects this condition and clears all the current data in the volumetric buffer. This results in temporary loss of picture data requiring approximately 10 seconds to recover, assuming that erroneous data is not continuing to be received. Should position data continuously jump more than 5 nautical miles at intervals of less than 10 seconds, then the weather data could remain cleared for extended amounts of time, such as the example here on the right side. Taking a look at unflagged erroneous altitude now, again, because altitude is used to determine height above terrain for the radar return, then as with erroneous position, erroneous altitude can result in excessive ground bleed through or missed weather detection. Additionally, it can result in incorrect modes and vertical situation display picture data, such as weather displayed at wrong altitudes. One secondary effect of erroneous altitude is an erroneous calculation of the radar horizon range, beyond which true terrain returns are not possible. And lastly, on a fourth example, if the altitude is erroneously low, The system will assume that the radar horizon is closer than actual, resulting in ground returns between the erroneous and true radar horizons to be displayed as a band. Generally, there are multiple sources for position and altitude available to the weather radar. The source availability and source selection priorities are aircraft platform dependent. Flagged invalid GNSS data will in those cases cause the radar to revert to the next available valid source for position and/or altitude. It is possible that the next available source would not have the accuracy that GNSS provides, and thus could lead to some increase in ground bleed through, depending on terrain characteristics. For example, more ground bleed through could be expected in mountainous terrain. If all sources of position or all sources of altitude are invalid, the weather radar will issue an in-op fault message to the flight crew. All right, and here is the last topic, or at least the main topic for the webinar, and then we can move to more of a close and answer any questions that remain. So let's talk about late weather detection as the last main topic, and more so some techniques that can be used if you are noticing some late weather detection challenges. So be aware that at certain tilt angles, only a portion of the beam may be intercepting weather and another portion intercepting ground. This may be a common scenario with precipitation only near the ground, with the actual weather being misclassified into the ground buffer mode. Since ground clutter reduction may not be perfectly correct all the time, when in doubt, we do suggest to examine both weather and ground map modes to see if the radar return is being put into the wrong buffer. In general, the antenna beam is narrower at closer ranges, and like we discussed before, it widens significantly at longer range. Therefore, the resolution and accuracy of the weather reflectivity is better at ranges that are closer to the aircraft. Several operators have reported either missing weather radar data on their display or targets with reduced reflectivity, typically at ranges between 50 and around 100 to 120 nautical miles ahead of the aircraft. So we've heard this, this concern, like, we are in weather mode and do not see anything displayed. How can we tell the radar is operating normally? How can this be verified? Unless you are flying completely over water, out to a maximum of 320 nautical miles, like all water, using the ground map mode, you can, as a quick method, determine the approximate detection range and verify whether the radar is properly functioning and detecting weather when present. Remember, as the radar processes radar returns being received, its processing software distinguishes the difference between radar returns from weather targets and ground terrain targets against that internal terrain database. Based on this internal filtering process, it places these two returns into two separate internal memory buffers. One buffer is for weather related to radar returns, while the other buffer is for ground terrain related ground radar returns. So occasionally, the radar could misclassify the weather returns as ground terrain, which causes the radar to place the weather returns in the ground terrain buffer instead of in the weather buffer. So let's maybe just in this example. So in this example, at least, over large areas of open water, just east of Florida area over the Atlantic Ocean. Move down here. There. So in the ground map mode on the right, you can see that the area is showing a return over the large island areas as well as over Miami, but this ground map mode is also showing a line of thunderstorms. When an area of misclassified low altitude weather eventually approaches to within approximately 50 nautical miles ahead of the aircraft, the radar then should classify correctly. As part of the upcoming late weather detection improvement, future software is updating scan rate speed and reverting back to an altitude-dependent gain, regardless of if the weather is convective or not. And so we are certainly looking at certain things to further enhance any situation which may lead to a late weather detection situation. All right, we can wrap up and let's discuss additional resources available to you after this webinar. But first, I'll stop here. And Eric Anderson, were there any other questions that had come up that we can respond to?
Yeah, there are some additional questions in the window. So first of all, Carl Johan, I'm going to put the answer to your question directly in the QA window with the link that you'll attend and some search keywords to use. The presentation should be posted by Friday, close of business, given the time it takes to get through our systems once we release it. Then there is a question about, Roland's been answering the questions directly. There's a question about what is the upcoming solution for GNSS jamming spoofing effects on the weather radar system? Eric, do you have any discussion about that?
I might be able to cover that, Eric Anderson. So we're looking at a variety of solutions, working with the OEMs. Inertials are a part of it. GNSS sensor warning flags are a part of it. EGPWS is a part of it. So there is basically a basic solution followed by a better solution and then eventually a best solution. So we're in pretty detailed discussions with a variety of OEMs right now to figure out what's best for each aircraft type. And essentially what will eventually end up happening over the longer term is the systems themselves will be able to see when the GNSS is flagging that the event is happening, and they will play through better than they do today.
Okay, thank you, Jason. There's a question, when is the TSO 3.0 available for the AW139?
I don't know if Ryan's listening. I know he's.
So someone else had asked this question in the chat. So TSO3 is actually available right now for AW139. I know Roland is texting into the answer as well. Roland, if you wanted to give some insight verbally on the phone, you're more than welcome to.
Yes, I was actually just typing. The STC for that TSO is actually available right now. So I think we should be taking order for that upgrade.
Yeah, and I think and I'm trying to remember who actually had asked the question that I had responded to, but as far as TSO1, TSO2, and then the enhancements to TSO3, just so that everyone's aware, we are actively working on a TSO4 campaign now with an expected completion maybe end of Q1 that will unlock some additional features that we'll be advertising here soon, along with some other little fixes along the way. And that'll be across both the commercial helo as well as the BGA fixed wing platforms.
And I think I'll also mention that Ryan and I and several of us internally within Honeywell, we were successful in advocating for ensuring that any of the fixes that we're releasing are available to RDR-7000 customers at no charge. So that doesn't mean if you haven't ordered options previously, you won't pay for options. If you get options in the later loads, you still have to pay for the options. However, any fixes or improvements to the radar system will be free of charge. We appreciate all of you as customers. We appreciate you trusting us with your radar technology, and we felt it was best for customers to offer those improvements and fixes, not options. Those are still for charge, but offering the improvements and fixes free of charge. So please work with your sales reps or with your field service engineers or OEMs as appropriate to try to get in line for getting the latest software on the radar.
Thank you, gentlemen.
By the way, I'm sorry, one other thing, Eric. The TSOs that Ryan and Roland are both referencing, some of the customers like Pilatus is one example. They use numbers for the software loads. We can certainly get you more information off the webinar for what that is, and that's unique to each OEM. So forgive us if that doesn't align with what you guys remember hearing as an example, 510 software or other versions of Pilatus software. And Eric certainly, Eric Anderson is certainly well versed in that. I would like to try to give Eric Tobler and Roland an opportunity for any of you who are still on the webinar. Thank you for your time today to ask more specific questions about either pilot technique or maintainer type questions. And we'll certainly quickly follow up with all the other questions. Eric, were there any other pilot technique or maintainer type questions?
Well, there's a question about, is there any value in having a 24-inch antenna installed on an aircraft with a service ceiling of 25,000 feet? Radar horizon will be just 200 nanometers.
So
nautical
actually,
nautical miles, not nanometers.
Yeah.
It's nautical miles. But so I was on the call yesterday with Eduardo. Good evening, Eduardo. It was a pleasure to meet you yesterday on the phone. I'm going to go ahead and say no. And I know that we had talked about the actual type design that you're looking at. At some point, I think we're going to need to have a more high level discussion with your representatives to go over that, because quite frankly, I don't see the necessity of having that large 24-inch dish, maybe 18, but it's going to be a toss up between the 18-inch dish and the 12-inch dish. Again, the 12-inch dish with the later TSO levels is going to provide all the same functionality and bells and whistles as the 24-inch dish does today. So
one quick,
yeah,
I'm sorry, Ryan, one quick thing, and Eric covered it earlier in the presentation. So it really comes down to your operation. So if you think about this as a pilot, it's time to detect weather and range of detecting weather. And certainly from a hazards, predictive hail, predictive lightning, predictive turbulence perspective, the larger the antenna, and Eric had this in the chart earlier in the presentation, the better. However, it's always a balancing act. So you're going to have higher costs. You're going to have installation challenges. Generally speaking, and Roland will say this over and over and has for decades now, the larger the antenna, the better. But it's not always necessary. If you're flying an aircraft on a typical domestic type mission, 18-inch antenna is perfectly adequate.
Thank you, gentlemen. There's a couple more pilot technique questions. First of all, how is the former beacon mode replaced in RDR-7000 on low-level flying? Ground map seems not to be updating fast enough.
Roland should talk to that one.
Yeah, and I need to quickly answer this before I jump over to my next meeting. So the beacon mode, we actually don't really have a true replacement for it. Meaning RDR-7000 can't really do beacon mode. What we offer is a high resolution ground map mode. So when you say the refresh is not fast enough, I assume you may be still attempting to do the low resolution ground map using the VB configuration. We do have a maritime option that you can go look at, and that offer high resolution ground map in a real beam display mode, so that you're getting response as the antenna scanning, rather than the VB configuration where the scanning is done independent of the display. So there's a delay in collecting that data and merging it into 3D buffer, and then extracting from the 3D buffer to the display. So there are pros and cons with each thing. But if you want fast update, the maritime option would be the one that you want to do. That one, in addition to a real beam display, you can also select sector scan. So the refresh, it's to the narrow plus or minus 30-degree sector. And it would mean that, like, every second, you should be having refresh display.
So then the final question is on the PC-24, is there any way you can reset the weather radar in flight? We've had multiple failures on the 24 where you get a WX fail. There don't appear to be any checklist to reset it, and the electronics CB gets locked out in flight.
Eric, please say that one more time. Forgive all of us for that went really fast.
Yeah, I don't know about that. I think we may need to do a little bit of research on the PC-24 operation manual before we can give you the answer.
All right.
Because I certainly
We
don't.
certainly are going to have to research it, but do you mind just stating it one more time clearly, Eric?
Sure. So the question is on the PC-24, can you reset the weather radar in flight to reset the weather fail fault message? There don't appear to
Okay,
be.
so this is I can talk a little bit to this, Roland. There's a very specific instruction in the Pilatus manual, and this is done for certification reasons with respect to which breakers can or cannot be reset in flight. And so generally speaking, unless it's in a procedure like an emergency checklist as a response to the WX fail ICAS message or CAS message, you should not be resetting the breakers. There's a little general rule in the manual that says, assuming it's not this type of a system, you can reset it once. There's some timing involved and that sort of thing. But my recommendation is to look at the manual. Failing getting a specific answer out of the pilot's manual, please reach out to us and we can coordinate with Pilatus and get you a good answer. Hopefully that's helpful, at least in the interim. And certainly longer term, we can try to get you a better answer.
Thank you, Jason. So that's all of the pilot related questions in the chat.
And next time we'll do the maintainers first and then the pilots, Eric. I'm sure we've got some maintainers and technicians on this call, and we rely on all of you every day, and we appreciate all of you. Any maintainer or technician questions?
No.
Okay.
No, but there's a couple other open questions. They're both kind of related. The first one being, when are we going to have a software update for PC-24? We were told there was one. So yes, there was. Our original TSO 3.0 was the software update to PC-24. There was a gremlin that was found after it was administered into Pilatus itself. Pilatus came to us. So that software has been pulled, and that will be part of the TSO4 fix that will be coming, like I said, mid Q1 2026 once we get FAA approval. We were actually well underway with it, but with the government shutdown, it did put about a month and a half's worth of delay, from a certification standpoint. So look for that with your Pilatus reps coming in the springtime. And then as far as Scott Martin's question, you took the update on PC-24. Does Honeywell pay to revert to the last version until a new fix is complete? Scott, I would tell you to reach out to your area customer support manager, and if you maybe provide me with your email or shoot me an email.
I've got it, Ryan. We know Scott. So Eric Anderson and I can work this one.
Yeah.
And make sure Scott gets taken care of.
Okay. Yeah. Perfect. Those were the only other two open questions that I saw.
Excellent.
Thanks, Ryan.
All right. Well, special thank you to Eric. Great job today.
Can you still hear me?
Yes, we can.
Okay, yep. Here, I just have a few more things if you can still hear me.
Yep, go for it.
Okay, thanks. All right, let me just go to the next slide. Here we go. Okay. All right, so just a couple friendly reminders here via pilots.honeywell.com and virtual classroom. You can find many different pilot guides, training videos, and familiarization items. And again, available on the pilot portal. You can find very specific pilot guides for RDR-4000, RDR-7000, both fixed wing. We have rotorcraft ones as well. And in general, along with many different videos covering similar topics, including advanced analysis modes, previously recorded webinars, and etc. Pilot guides include additional operating details, as you may know, basic principles of weather radar, and more information about your specific installation. So we definitely, would like your feedback on this webinar. Please let us know if you would find interest in any further exploration of topics such as these, details of any of the following, understanding radar beam width resolution, long-range weather analysis, and stratus weather analysis, understanding weather radar horizon, diagnosing interference patterns, radar radome confidence checks, and failure modes that do not have a fault detection or notification for the flight crew. Things that, yeah, definitely would like your feedback and understanding on how we can best support you out in the field.
Right. And just to expand on what Eric just said about it, if you could go back to that last slide real quick, Eric. Eric, I think we have a means for everyone who attended today to email us.
Yeah.
I would love to see, if anything's not listed on the slide here, you see, this is just a means of prompting a discussion. So as an example, I know a few of you on this call as customer pilots who are out flying the radar are actually pretty well along in your understanding of how to use this radar correctly. You may want other details in an advanced radar webinar, which we're building now. And so please reach out, email us. This is what we'd like to see covered in an advanced radar webinar. What we did today was more of a basic type radar webinar, and we will be sure to include that. So thank you, everyone, for your ideas and thoughts. We'll do our best to address those.
Thank you, Jason.
Gentlemen, a couple of final questions. One, are the pilot guides available to maintainers with our login credentials?
Yes, they are. As long as you have a valid Honeywell login credential, if you're part of a maintainer organization, MRO, dealer, channel partner, et cetera, you should be able to access, like for example, RDR-7000. I would just say when you go to our Tech Pubs portal, just type in RDR-7000 in the search bar, and you will see the interview, pilots guides and familiarization tools. They should be readily available.
Thank you. And then a question, can there be a rotorcraft specific webinar with GMAP and related modes? So I think that's some feedback for Eric and Jason.
Absolutely. I'm personally, and I'm sure other team members would be as well, although I can't speak for them, very interested in seeing your needs met as helicopter operators. And there certainly are some unique aspects there. And Roland gets out a lot to various large operators, but it would be great to get Roland connected with all of you as helicopter operators. You're certainly a super important aspect of our our business, if you will, and helicopter operators have unique requirements. So yes, we should do that.
And then the last question was about who to contact with PC-24 specific questions. And I'll just say to anybody remaining on the phone, if you have any questions about the use of the radars, in-service issues with the radars, you can feel free to email me. My email is in the question and answer session now.
Well, Eric, so someone else had actually emulated that question, and I had answered it a couple of minutes ago. I did provide the Aerotech Support 800 hotline number with the option for avionics, to get a case going. That way, if you are experiencing issues out in the field that we may or may not have heard of as of now, it's important, it's crucial that we get a case open so that there's data and history of it, so that if there are new things, even old things that may be popping back up that we have to work into later fixes and bug patches, it's important that we have some semblance of pedigree. So I would definitely advise everyone, contact Aerotech Support. I did answer that question about 4 minutes ago in the group Q&A with the telephone number. Very, very vital that we do that. It's, there's also on our technical support landing page, there is a request technical support web form box. You can always click that and put in all the correct aircraft information, what's going on, etc. Either way, a case will be started and there will be historical data that we can actually work from versus, quite frankly, a little bit of hearsay. So definitely important to give a call to Honeywell, to our tech support team, so that we can start collaborating internally to come up with a solution.
Thanks, Ryan. And I would like to encourage anybody who feels like they're not getting sufficient response from submitting cases at Honeywell feel free to reach out to me directly and I'll handle your issue. Thank you.
All right, thank you, everyone. And in closing, Jennifer, we're going to make sure the Q&A somehow is included as part of the recording, or we'll figure out a way to post that somewhere so everyone has the benefit of the Q&A answers. Thank you again. Big thank you to our customers. We are here for you. You are appreciated, and we're looking forward to being able to do this again in the future. Thank you so much, everybody. Have a great rest of your day.